Assalamualaikum girls. I'm Shamsunisa from Royal Degree College Chemistry Department. As we are talking about Unit 4 General Chemistry, in this today we'll deal with Chapter 5 Photochemistry. In this we'll start first session. We'll study about photochemistry, differences between thermal and photochemical reactions, laws of photochemistry, quantum efficiency or quantum yield, types of quantum yield, and reasons for low and high quantum yield. Photochemistry, the branch of chemistry which deals with the absorption of light radiations and its effect, that is physical or chemical, on the substance is known as photochemistry. Photochemistry deals those reactions which takes place by the absorption of photons of light radiation. From the photochemistry point of view, visible and ultraviolet radiations are important. Wavelength of ultraviolet light is 2000 degree angstrom to 4000 degree angstrom. Wavelength of visible light, its range is 4000 degree angstrom to 8000 degree angstrom. The processes involving the absorption of photons, that is light, are generally called photoprocesses. They are mainly of two types. First one is photochemical process and the second one is photophysical processes. So first of all, we'll talk about photochemical processes. Those processes in which the absorbed light causes to some chemical change in the substance are called photochemical processes. The reaction which occurs with the absorption of light are called photochemical reaction. Here you can see the example, photochemical combination of hydrogen and chlorine. Means in the presence of light, when hydrogen and chlorine will react with one another, we are getting 2 moles of hydrochloric acid. Another example of photochemical process is photosynthesis. Here in the presence of light, 6 moles of water reacting with 6 moles of carbon dioxide and we are getting glucose along with 6 moles of oxygen. Second process is photophysical process. Those processes in which a substance absorbs light and emits it without undergoing any chemical change are called photophysical processes. Example is fluorescence, phosphorescence. Now we will see the differences between thermal and photochemical reactions. Photochemical reaction, thermal chemical reaction. These photochemical reactions, these reactions takes place by absorption of light. And thermal chemical reaction, this takes place by the absorption or evolution of heat. So here in the photochemical reaction, free energy change, that is delta G, is not negative in all cases. Example, in photosynthesis, delta G value is positive. In the thermal chemical reaction, delta G is always negative in this process. Then in photochemical reaction, the required activation energy is gained by the absorption of photon. And in the thermal chemical process, the activation energy is gained by molecular collision or by the absorption of heat. And here in the photochemical reaction, temperature has no significant effect on rate of a reaction. But the temperature has the effect on rate of a reaction where in the thermal chemical process or the thermal chemical reaction. It takes place only in the presence of light. Which reaction will take place only in the presence of light? Photochemical reaction. And the thermal chemical reaction will take place in dark also. Then next difference is it produces changes in the electronic state only by discrete jumps. Which changes? Which will produce the changes in the electronic state? That is photochemical reactions. But here in case of the thermal chemical reaction, it produces continuous increase in energy. Next difference is visible and ultraviolet radiations cause excitation of electronic states from bonding molecular orbital to anti-bonding molecular orbital, where in case of the photochemical reaction. But in case of thermal chemical reaction, causes increase in the vibrational and rotational states, also in addition to increase in the electronic states. Now we'll see about laws of photochemistry. All photochemical reactions are governed by two basic laws known as law of photochemistry. They are, first law is Grotthuss-Draper's law, which is also named as primary law. Second is Stark-Einstein's law of photochemical equivalence. Now we'll see the first law, that is Grotthuss-Draper's law or primary law. This is also called the principle of photochemical activation and also called first law of photochemistry. This law was proposed by Grotthuss theoretical and confirmed by Draper experimental. Now we'll see the statement. Only those radiations of light which are absorbed by the substance or reacting system can only lead to the photochemical reactions. Here IA it is equal to IO or I0 minus IT. So what is IA? IA is the intensity of absorbed light. IO is the intensity of incident light. And IT is what? Intensity of transmitted light. It does not mean that the complete absorbed energy is converted into photochemical reaction. Some of the radiation may be utilized. Example, when light falls on potassium permanganate solution. It absorbs light radiation but does not undergo any chemical change. This phenomenon is called photosensitization. All the light radiations absorbed may not be effective to cause the chemical change. The absorbed light may produce the following changes. What are those changes? The first one is the absorbed light may simply convert it into heat energy, or the absorbed light may be re-emitted as a light of different wavelengths causing phenomenon like fluorescence, phosphorescence, etc. And the third one is the absorbed light may be transferred from one substance to another substance, which then undergoes chemical change called photosensitization. Now we'll see the second law, that is Stark-Einstein's law of photochemical equivalence. This law is also known as principle of quantum activation or second law of photochemistry or law of photochemical equivalence. Einstein applied the quantum theory of radiation to photochemical process. This law explains the existence of photochemical reaction with the amount of light energy absorbed. Here we'll see the statement. In a photochemical reaction, each atom or molecule of reacting substances absorbs one quantum, that is one photon of the radiation. That is, we can write the equation like this: E it is equal to h mu. E it is equal to what? Its value will be one quantum energy. Energy of Avogadro's number of photon is called Einstein. So E it is equal to nh mu. So here E it is equal to nh mu. Since here the value of mu it is equal to c by lambda. So in this formula, in place of mu, we are writing the value of mu, that is c by lambda. Rest of the things are as it is. Where n is called the Avogadro number and its value is constant, that is 6.023 into 10 to the power 23. In each photochemical reaction, 1 mole of the substance dissociated by absorbing 1 Einstein energy. According to Einstein's law, each mole of a reacting substance absorbs 1 Einstein of energy. So energy of 1 Einstein, we'll see, that is its formula is E it is equal to NHC by lambda. Okay. where n is Avogadro number. Its value is 6.023 in 10 to the power 23. H is the Planck's constant. Its value is 6.625 into 10 to the power minus 27. And C is the velocity of light. Its value is 3 into 10 to the power 10. By substituting the values of N, H, C in the above equation, we get like this. Heat is equal to, in place of N, we are writing its value 6.023 in 10 to the power 23. And in place of H, we are writing its value as 6.625 in 10 to the power minus 27. In place of C, we are writing its value 3 into 10 to the power 10 divided by lambda. Now, we are multiplying these values. 6.023 into 6.625 into 3. So, you will get this value, that is 119.70 into 10 to the power 23 as it is, 10 to the power 10 we are writing that is as it is, and then 10 to the power minus 27. Now, 10 to the power 23, 10 to the power 10. We are adding these values, so we will get 10 to the power 33. Rest of the values are as it is. Now, 10 to the power 33, 10 to the power minus 27. We are subtracting. So, we will get the value as 10 to the power 6. Now, we are writing like this, see here, if this point, now 119.70 is there, na? If this point we are bringing towards one digit towards the left hand side. So, here 10 to the power 7, one digit will increase. So, we will get the value as equal to 11.97 10 to the power 7 by lambda arcs per mole. And the E Einstein's value in terms of joules per mole, the value will be like this. That is 11.97 by lambda. If we are writing in terms of kilojoules per mole, the value of Einstein will be this much, that is 11.97 10 to the power minus 3 by lambda. These are the constant values. Quantum efficiency or quantum yield. Quantum yield gives the relation between number of moles of reactant taking part in a reaction and the number of Einsteins absorbed. The number of moles of reactant reacted per Einstein of light absorbed is called quantum yield. The ratio of the total number of moles or the total number of molecules transformed into products and the total number of photons absorbed in the process is known as quantum efficiency. So the quantum yield is the ratio of number of moles reacted to the number of Einsteins absorbed. It is denoted by phi. So we can write the formula like this. Phi, it is nothing but quantum yield. Okay, that is equal to number of moles reacted in a given time divided by number of Einsteins absorbed in the same time. Or we can write like this also, phi, it is equal to number of reacting molecules divided by number of quantum absorbed. Now we'll see about types of quantum yield. Quantum yield are of two types. They are normal quantum yield, abnormal quantum yield. First we'll throw light on normal quantum yield. So according to Einstein's law, for each Einstein energy absorbed, only one mole of the substance should be involved in the reaction. Then the number of moles reacting is equal to number of Einsteins absorbed and the quantum yield should be unity, that is equal to 1. This is known as normal quantum yield. Next, second type is abnormal quantum yield. Only in few chemical or the few photochemical reactions, quantum yield is close to unity. But in many cases, quantum yield found to be higher than 1 or higher than unity. The quantum yield higher than 1 or lower than 1 is collectively called as abnormal quantum yield. This abnormal property was explained on the basis of the fact that a photochemical reaction takes place in two steps: primary process, secondary process. First of all, we'll see the step first, that is the primary process. In this process, each molecule is activated by absorbing one quantum of radiation and forms activated atom or activated complex. Second process is, in this process, the activated molecules may undergo either of the following changes to complete the reaction. First one is it may react to form final product. It may partly or completely deactivate it and thus no further reaction occurs. And it may cause many molecules to react through a chain mechanism. Now we'll see about reasons for low quantum yield. What are the reasons for low quantum yield? That we'll see. The low quantum yield is due to the following reasons. The first one is deactivation of the photochemically activated or photochemically excited molecules before they react. Insufficiency of the sum of the absorbed quantum to activate some of the reacting molecules. Third one is recombination of some of the dissociated fragments of the excited molecules to give back the original molecule. Example we see here, photochemical combination of hydrogen and bromine to form HBr, that is hydrogen bromide. Second example is the photochemical combination of, in that only we are seeing, in that example only, photochemical combination of hydrogen and bromine requires a radiation of wavelength less than 5000 degree angstrom for the primary process. Here you can see the reaction, hydrogen reacting with bromine, and we will get 2 moles of hydrogen bromide. This is a photochemical combination. In the presence of light, this reaction will take place, and how much phi value it is showing, that is the quantum yield is here 0.01. So the quantum yield for this particular reaction is very low. You can see here the value is 0.01. This quantum yield can be explained by mechanism. Now we'll see the mechanism. The first step is primary process. On photolysis, bromine absorbs light and dissociates to give bromine free radicals. Here you can see bromine. In this, light is falling. Bromine is going to absorb the light energy, and as a result of that, it is showing the dissociation and will get the bromine free radicals. Then second step is secondary process, in which what is happening, we are taking hydrogen molecule, it is made to react with the bromine free radical, and we are getting HBr along with this hydrogen free radical. It is our first step. In the second step, this hydrogen free radical, it is combining with bromine molecule, and we are getting hydrogen bromide and bromine free radical. This is our second step. So the third step is we are taking hydrogen free radical reacting with hydrogen bromide, and we are getting the hydrogen molecule and bromine free radical. Fourth step is bromine free radicals. Both the bromine free radicals will react, and as a result of that we are getting bromine molecule. This is our fourth step. So the reaction 1 of secondary process is highly exothermic, which is the reaction 1. Hydrogen molecule reacting with bromine free radical, we are getting hydrogen bromide and hydrogen free radical. This reaction is exothermic reaction. During this reaction, no, that one is exothermic or endothermic. That is highly endothermic reaction. During this first reaction, the amount of heat is going to be absorbed. This is the endothermic reaction, the first reaction. So it takes place very slowly at room temperature. Hence the reactions second, third, fourth are depend on the reaction 1 are taking place very slowly at ordinary temperature. So the reaction 4 is just reverse of the primary process. See here reaction 4th. It is the reverse of primary process reaction, isn't it? So here in this, the bromine atoms formed in the primary process do not form HBr. Instead, they combine together to give back bromine molecule. Consequently, the quantum yield of the reaction is very low. How much? That is 0.01. Reaction 1 is endothermic. So its rate can be increased by increasing the temperature of the reaction. If we increase the temperature of the reaction, automatically the rate of the reaction will increase. So the quantum yield of the above reaction increases with increase of temperature. Next we'll see about reasons for high quantum yield. The higher quantum yield is due to the fact one quantum of radiations bring about transformation of more than one molecule of the reactants. Here the photochemically activated molecules initiates a sequence of reactions. As a result, several molecules undergo reaction, although only one quantum of light is absorbed by the reactants. Example we'll see here, photochemical combination of hydrogen and chlorine molecule to form hydrochloric acid, which shows very high quantum yield. How much quantum yield it is showing? 10 to the power 4 to 10 to the power 6. Here you can see the reaction, hydrogen reacting with the chlorine in the presence of light, and we are getting the 2 moles of HCl. Here the quantum yield, phi value is equal to 10 to the power 4 to 10 to the power 6. That is high. So the high quantum yield of this reaction is due to what? Due to chain mechanism. Now we'll see the mechanism. In that the first step is primary process. In this process, chlorine dissociates into chlorine free radical. Okay, chlorine molecule, it is dissociated to form chlorine free radicals by the absorption of radiation of wavelength 4800 degree angstrom. Here you can see the reaction. Chlorine molecule, it is absorbing light, that is H mu, of wavelength 4800 degree angstrom, and we are getting the chlorine free radicals. Okay, this is the chain initiation step. First step. Then the second step of the mechanism is secondary process. The chlorine free radicals formed in initiation step react with hydrogen molecule to form HCl and produces hydrogen free radical. So the hydrogen free radical reacts with undissociated chlorine molecule to form hydrochloric acid and chlorine free radical. You can see the reactions here. Chlorine free radical reacting with hydrogen molecule, we are getting HCl and hydrogen free radical. Then hydrogen free radical reacting with the chlorine molecule, we are getting HCl and chlorine free radical. This step is chain propagation step. Some free radicals combines to form reactants or products and inhibits the chain reaction. Inhibit means it will stop the chain reaction. This step is called chain termination. You can see here hydrogen free radical, chlorine free radical. When they are reacting, we are getting HCl. With this, the chain will stop, chain terminate. Then hydrogen free radical, then combine. We are getting hydrogen molecule. Here the chain will terminate. Chlorine free radical, if they are reacting, we are getting the chlorine molecule. These are the chain termination steps. So due to this chain reaction, quantum yield, that is phi, is very high. How much? 10 to the power 4 to 10 to the power 6. Thank you for listening my lecture.